So we left off last week just talking about confidence intervals. Okay, so and today we're going to get just even more into confidence intervals. Okay, and we're just kind of really beat this to death. All right, so we just learned how to calculate a confidence interval, and we say, we take a sample, take some sample, and from that sample we find the sample mean, y bar, and we find the sample standard deviation, s. It's hard to write and talk at the same time. Sample standard deviation, s. And based on this, we create an interval. That's going to be y bar plus or minus, and I put in t star, okay, or this is our critical t. Times s over the square root of it. Okay. All right, and this is how we find our confidence intervals. Okay, and so we would say something like, if we took n is equal to 10, we took a sample of size 10, okay, and we found the mean of this sample. So let's say I don't know what's a good what is something we're interested in? Weight of cats. Okay, so we take 10 random cats. All right, feral cats, angry, and we gather them, and we measure how much these cats weigh. So I don't know. How much does a cat weigh?
No idea.
10 pounds? 5 pounds?
10 minus a pound. 5 pounds. That's tiny. 10 pounds.
10
like
pounds?
10
pounds, right? We've seen like Garfield cats, right? So maybe this cat, the average maybe is 10.2 pounds, okay? And we take the standard deviation, and maybe the standard deviation of this sample is 1.5 pounds. Okay. All right. So what can we say based on this? Can we say something about the population and the total population of cats? What is the average weight? What is the average weight of a cat? What is the average weight of a cat in the population? Okay, and so this is our sample of 10 cats. And of course, there's some assumptions that went into this. We're randomly picking these cats. Okay, how you actually randomly select cats is a bit of a mystery. I'm not sure how that could actually.
Randomly select you.
They'll cats randomly select you. They call the shots, don't they? So, all right. I'm allergic to cats anyway, so even worse. All right. What is the average weight of a cat in the population? So we're going to make a guess about the true average weight of the average cat's weight in the population. So we're going to make a statement about mu. Okay. Mu based on our sample. And the reason why we can make a statement about mu based on our sample and say something with such a kind of this precise formula here is because we know that if the population has some mean and some standard deviation, every time we take samples, the sampling distribution should follow a normal model. And because we know the properties of the normal model, we know that most of the time our random samples will produce sample means that are close to the population mean. Okay, that's why we can do that. Okay, so again, the reasoning for our confidence interval is that so sampling distributions showed us that when we take random samples, sample mean is usually close to the population mean. In fact, we can call this the model follows a normal distribution. Okay, so in this case, we say our confidence interval. So maybe we'll make a 95% confidence interval, and here again the formula is y bar plus or minus t star times s over the square root of n. So y bar is 10.2. And then I'm going to go plus or minus t star, which we will look up in a moment, times s, which is our 1.5, divided by the square root of n, so square root of 10. Okay. And so this t star, this is going to be t with degrees of freedom equal to 9, because it's always n minus 1, with 9 degrees of freedom. And for a 95% confidence interval, we use alpha is equal to 0.025. All right, basically it just means all right, just our critical value, because if we're going for the middle 95%, then that means we have 2.5% over here and 2.5% over there. So the book calls it 9.025, but I just like to call it critical T. And we can find this easily by looking at the T table. We go to 95%, and we go up to 9 degrees of freedom, and we have 2.262. Okay, so we have this thing is equal to 2.262. So now I have a confidence interval, 10.2 plus or minus 2.262 times 1.5 over the square root of 10. And what does this give me? 2.262 times 1.5 divided by square root of 10. So now I have 10.2 plus or minus 1.07. So if I add 10.2, on the upper end I have 11.27, and on the lower end I have 9.13. say I am 95% confident that the population mean, alright, so again we're making a statement about mu, not about anything about our sample, okay, because we already know what our sample looks like. We actually have all 10 measurements for our sample, okay, but we're going to say something about the population mean, and I say I'm 95% confident that the population mean, so really it's the average cat weight in the population is between 9.13 pounds and 11.27 pounds. Something like that. Alright, is this okay? Alright, so we say we're saying 95% confident, okay? This is not a probability statement, okay? It's not, there's a 95% chance that the population mean is between here and here, okay? Because the population mean is fixed, okay? We treat that as something that's fixed, okay? So if we were magically able to gather all of the cats in the world, or in the United States, or even in the country, okay? Or I guess that's the same in the United States, or in the county or something, if we were able to gather all of the cats and weigh all of them and take their average weight, that's the population mean, okay? That's not going to change. That's not like some random value. That's fixed, okay? The population mean is fixed. Okay? We've taken our sample and we've observed our data. Our data is also is no longer random. Once we've observed it, okay, our observed data is not random either. Okay, so the population, the mean in the population, the average cat weight, it doesn't care what our sample looks like. Okay, and our sample, based on our sample, we create this confidence interval, but we're not. But the population mean doesn't care. We've created this confidence interval. The population mean is either going to be contained in this interval, or it's not going to be contained in the interval. Okay? This 95% confident, where this comes from, is coming from the idea that if I were able to repeat this process of taking 10 random cats, figuring out the mean and the standard deviation, and creating a confidence interval, if I were to do this over and over and over again, 95% of the time, whenever I make the interval, I would have actually captured the true population mean. Okay, I would have captured it. And 5% of the time, just because my random choosing was weird or obscure, I happened to get something that's odd, and the confidence interval I produced that time is going to be wrong. And so about 5% of the time, I make the mistake that where my confidence interval does not actually contain the population mean. Okay, is that kind of, is that okay? So I'll write this down, and I'll let you guys think about it for a second, and then I'll do some demonstrations on the computer that might, I hope, will clarify what's happening here, okay? So, the 95% confidence, that comes from, let me write this up here. Okay, so 95% confident that means is, if I were to repeat this process many times, which is take a random sample and then find the, then make a confidence interval. Okay. About 95% of the time, the intervals I make will contain the population mean, and 5% of the time it will not.
The process of randomly sampling.
Yeah, so because again, all I'm doing is I'm just randomly picking from this population, right? Yeah.
Just a little bit earlier, what does it say under T up there? By T?
Which T?
The one below the arrow? Yes.
This is DF, degrees of freedom equal to 9, alpha equal to 0.025. Yeah.
Population mean is 10.2?
No, we don't know what the population mean is. This is my sample mean. This is sample mean, okay? So again, this is what we're going through when we do try to do statistics in the real world. This is what we're faced with, okay? If I asked you, what's the average height of a male in the United States, you'd have an idea. You'd say like 5'9", 5'10", something around there. But we actually don't know what the average height is, okay? In order to figure out the average height, we would need to find every single person or every single male, take their height, and then average them, okay? We can't do that. All right, so what we do is we take a sample, and based on this sample, we're going to try to make a statement about the average height of the population. Okay, so again, here we don't know what the population is. Okay. All right, so what I'm going to do is I'm going to do a simulation, all right, where we actually know the population, okay, but we're going to create confidence intervals as if we did not. Hope this works. Okay, so I've used the random normal function, rnorm, to just generate 100,000 people. Okay, and this is going to represent our population. We've got 100,000 people in our population, and I don't know if all of this R notation is weird and stuff, but basically this little arrow says store all of that into this box called population. Okay, and we can take a peek at population. Okay, now if I actually just typed at population, it would spit out 100,000 things. But we don't want that, so I'm just going to say like, just show me the first 10. So I'm just saying, show me 1 through 10. And the way I generated the population is that the mean is 0 and the standard deviation is 1. Okay, so our population mean is 0, and I can actually ask what the mean of the population is. Okay, it's actually very close to 0. It's 0.002334. Okay, that's the true population mean. Okay, and the true standard deviation of the population is 1.002248. Okay, and we can ask for a histogram of the population, and I'm going to just add a few more breaks to make it a little bit smoother. Oops. That, but Alright, so anyway, this is our population. And, it looks like that. Okay, so you can see the mean is at 0 and whatever here. Okay, so what I'm going to do is we can take a sample using the sample function, and I'm going to store this in something called SMP, and I'm going to sample from the population, and I'm just going to select 10 people out of the population. Okay, and the 10 people, if I look at them, these are, or not the 10 people, but the 10 items that I've selected. Okay, so again, the population has mean 0, standard deviation 1. The 10 items I selected from the population are these guys, and I can calculate the mean and standard deviation of my sample. Okay, so if I take the mean of this sample, that mean is 0.32, and the standard deviation of this sample is 1.13. And based on this, we can create our what do you call it? Our confidence interval, right? So in all of these cases, as long as I'm drawing 10 from my sample, or as long as my sample is size 10, then my critical T is going to be the same, right? Because I'm going to always have 9 degrees of freedom, and if it's always going to be a 95% confidence interval, my critical T is always going to be 2.262. 95% critical value. So I can just, I will call something called critical. My critical value is going to be 2.262, taken from my table. And so the lower end on the confidence interval will be the mean of my sample minus critical times the standard deviation of the sample divided by what? Square root of 10. Is this okay? What I've done here? Alright, so this is just, all I've done is taken the formula for the confidence interval, and I take the mean, subtracting off t times s over the square root of n. Okay? And I can create the upper end by doing the same thing, except it's going to be mean plus the critical value. Okay? And so here you can see that because the sample mean that I've selected is 0.32, so we're somewhere over here. When I created my confidence interval goes from negative 0.5-ish to 1.1-ish. Okay? So my confidence interval goes from somewhere down here to somewhere over here. Okay? And I get a confidence interval. And does this contain the population mean? Yeah, okay, because the population mean is 0 or something very close to it, and we see that this number, 0.002, is indeed in between these two numbers. Alright, this is okay? Alright, so what I'm going to do is I'm going to have R create a whole bunch of these confidence intervals, and we're going to and draw all of them on the on our chart here. Okay, so I've print some stuff, but then I realized, I think we can do this actually. So let me, I'm going to just create an empty plot. Okay, and I'm going to just draw a line at the mean of the population. Alright, so this horizontal line represents the population mean. Just ignore this dot for now, okay? Or just ignore it when I produce. Okay, so this line represents our population mean. Okay, and so if I take a sample, let me just try this once. So I'm going to take a random sample, and then I'm going to plot. So if I ask for the mean of the sample, it's negative 0.55, and if I plot this dot at position 1, I would get a dot right there. Refresh this. Okay, and so can you guys see this dot? Yeah. Okay, so this dot represents the negative 0.55. This is the mean of the sample. Okay, and then I can calculate the upper and lower ends. Of our confidence interval, and I can draw basically a line representing what that is, okay? Alright, and so this is my confidence interval, okay? So I've gone, oh, actually I messed this up. Shoot. Alright, let me clear this out, okay, because I did critical value s divided by square root of 10. Okay. Divided by square root. Alright, sorry. Let me just do this again. Okay, so we've got this. I'm going to put a mean right there. Okay, I'll just do the horizontal line. Now, so I don't know if you guys can see it. Okay, but this is our confidence interval. This is our mean, and then we've created we've gone out whatever our standard deviation times 2.262 down and 2.262 above, and we see that indeed this confidence interval has captured the true value of the population mean. Okay, we're okay with this. All right, so I'm going to generate 100 random samples, each of size 10, and I'm going to calculate the mean of all 100 of those samples, and I'm going to just throw all of the dots onto here. Okay. Now we would expect most of the dots to be close to 0, okay, but a few of them will be far away, and maybe we might see ones that are really far away. Okay. Hope, this works. I haven't actually tested out my code. Oh, I didn't. Oh. I want to sorry, you know what, just to illustrate this a little bit better, I'm going to just put a tiny delay in between each sample, and you can see them, it'll do one sample, and then it'll do another sample, and then it'll do another sample, because if I just do all at once, it'll just go like, blah, alright, so, I gotta just look up the, little resource, and I just want oh, sleep, sys.sleep, that's what I want. Point. We'll stay point 3. Okay. Alright, I hope this works. Okay, so you can see it's just finding just different things there. I don't know if it'll work. No, it isn't. Okay, and so you can see each time it's just taking a random sample and it's calculating the mean of all of these random samples. So most of the time, when we do this, we're pretty close to the thing, okay? But then what we're gonna do now is we're gonna calculate for all 100 of these different, so each of these dots represents a sample of 10, and we've calculated the mean of that sample of 10, okay? And so I've got 100 of these samples of size 10, and we're going to produce confidence intervals for every single one of them, okay? Now that would be very tedious for us to do, right? Because we'd have to do plus or minus t times s over the square root of n, but R is a computer and it doesn't care, okay? It can just do all of this really quickly for us. So I'm going to do the same thing, and then, hope my code is right. So, all of this. So actually, oh no, I'll just leave that there, and then this work. Okay, so yes, so now you can see it's producing confidence intervals for all of these. Yeah, and so you see, yeah, this guy missed it, right? It's kind of cool. All right. Okay. Yes, we have a question.
Will we be required? Excuse me, sorry. Will we be required to know this coding for the
No.
midterm or the exam?
No. I won't make you do that. Maybe I'll have a lab where you guys do something, and I'll have a lot of code written up or something, and you
Like
guys
an
can try
extra
it out.
credit.
Maybe something. Okay. All right. So so I don't know. Maybe we can see how many of these actually missed the thing. Okay. Now you'll notice some of these have you know, the bars, like this one, the bars are huge, right? The bars are huge there, and this guy, the bars are tiny. What's going on? The standard deviation within the sample, okay? So when we drew 10 people, we happened to draw some people that were really spread out, okay? And so the standard deviations of our sample just happen to be really huge, and that's why the error bars are very big here, okay? And so, with this, maybe we can actually see how many we missed. So we got 1 that missed here, 2, 3. Ooh, maybe this is a 4. I don't know. 5, 6, 7, 8. Okay, so 8 of them happened to miss. Okay, so that's a little bit higher than what we would expect. Okay, but then again, we've only done 100, right? So according to our theory, out of 100 different confidence intervals that I create, about 95% of them, when I create the confidence interval, should capture the true average, okay, represented by this line, and about 5% of them would miss, okay? And in our case, 8% missed rather than 5 or 8, okay? And we could actually do, right? If now it's like a binomial problem, right? What's the probability of missing 8 if the true probability is 5% or something, right? Okay, 8 or more, or something like that. Okay, so we could figure that out, but no worries. But we could, we could do another 100, and we can try to count and see how many we miss and things like that. Okay, so again, the reason why the things changed so much was because our standard deviation changed from thing to thing. Okay, if instead, if I happen to know the population standard deviation, I could plug that in instead. Okay, now this would never happen in real life because there's almost never a situation where you don't know the population mean, but you know the population standard deviation. That almost never happens. Okay, but if somehow I knew the population standard deviation, okay, then what would we have? We would not have the t-distribution. We would have what? The normal distribution. Okay. Do you guys remember why we even used the t-distribution in the first place? Okay. Huh? Okay. So when we looked at sampling distributions, we knew that sample means followed a normal distribution. Okay. And you'd think we would just use numbers from the normal distribution, but we didn't. We had to look at this t-distribution. But the reason why we used the t-distribution was because there was that extra layer of uncertainty using the s from our sample rather than the sigma from the population. Okay, because of that extra layer of uncertainty, we had to kind of make our tails wider. Okay, so if my critical value, if I use the critical value from I can't think right now. From the normal model, I would have used 1.96. Okay, I would have used 1.96, and if I did that, too many of my confidence intervals would have missed the mark. So let me just demonstrate that very quickly. So it looks exactly the same, but I think if we counted how many missed, I think we would have more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so only a few more. Okay, but ones that before. Like this one, I think, I don't know, I don't remember which ones, but when I shrunk down my critical value to 1.96, we see a greater amount of our things missing the mark, okay? But that's because we're using S, and so if I wanted to use the critical value from the Z, instead of the standard deviation of the sample, I would use the standard deviation of the population. I think. This might explode in my face, I don't know. Okay, so here I use the population from, standard deviation from the population, okay? And now you notice that all of the bars are exactly the same width, okay? And so, in this case, even though now my critical value is 1.96, if I count how many miss, 1, 2, I think that's a 3, 4, 5, okay? Only 5 miss, okay? Even though I've shrunk the critical value here, alright? And that's because I'm using the population standard deviation rather than the sample standard deviation. So that reduces a layer of uncertainty, and we can see that fewer of our confidence intervals miss the actual population mean, even though the width of the bars is now limited to 1.96. Okay, I don't. Is that okay? Does this illustrate what's happening? Okay, so oh goodness. Yeah, we'll take a break. I think it's about time. So okay, so anyway, I hope that was at least kind of educational, the demo.